So yeah. So to YouTube Steam now. Oui. Okay. Test 1, 2, 3. Okay. It's all right. Oh no, why not? Oh. Oh my God, what happened? Oh, go to the new channel. Go to Zoom. Right. 1, 2, 3. Okay. Now this one. Let's we go to Zoom. Share the screen. Sure. Yeah. This one. Go to the right. It's M605. It's M605. M605 on physics and 2, 4, 5 like that. 20. This is 20. I need this one. All right. Okay. 1 minute in. No one is watching, right? current view is no one. Like that, right? Okay. Yes, there are. Yes, sir. So this is the substituted session for the mathematics subject by the teacher Natapon, right? So yeah, the time comes. I need to start right now. It's 12:40, right? And according to the replacement rate is M605 like this, and here is the time on at 12:40 Tuesday. Mathematics grades 33. I think it should be SCI, right? I'm not sure. Or math M604&M605. I'm not sure, but we're gonna take two periods for this subject, and we're gonna get back at 15:10, right, until 16. All right, and yeah, let's start our. I'm not sure whether anybody want to join the Zoom meeting, but anyway, if no one, we're going to use the same thing as the registration when you want to attend class. All right. Yeah. Let's start our lecture from the previous from the last time, right? Is right there. The Heisenberg uncertainty along the x-axis, right? That's what we have talked before during this semester. Yes, the broad wavelength has been already discussed, and what is that? The Heisenberg uncertainty along the x-axis here, right? This expression in 65. Well, the speed of an electron, right, has been already addressed in that problem. We're gonna reach the next uncertainty by Werner Heisenberg. It's the uncertainty in terms of energy and time. All right, in 65, you can see that the product of the difference between location along the x-axis and the momentum along the x-axis, the product of these two quantities, is always greater than, okay, or not less than h by 4 pi, or the half h slash, right? Yes, the yeah, it's the, okay, I'm not sure whether anyone want to join, because in M605 usually you want to join the Zoom meeting anyway. Yeah, but this one is quite it's the variation, okay? It's a little bit different from 65. It's the product between the energy uncertainty and the time uncertainty. So it's called uncertainty, Heisenberg uncertainty. Heisenberg uncertainty in terms of energy, which is the first term, delta E, okay? E denotes the energy, and time, right? You know that the variable T represents time, and delta is the uncertainty, the difference. Okay, and this is in the same way as the 65. The product between the quantity E, the energy, and the time T is always greater than h by 4 pi or h/2. All right. Delta E is the uncertainty of the energy in a particular state, and delta T is the time interval of the system that stay in that state. Okay, it's the observation time. Okay, the period of time you want to observe the energy in that system. Okay, in a certain system. You may not be completely able to understand 73. It's better for us to consider an example or a problem, a sodium, right? You know that sodium is denoted by Na, right? Yeah. Sodium atoms stay in a resonant state for an average time of 1.6 10 to -8 second. Okay. Yeah, it's in the resonant state, and the time they want to consider is 1.6 10 to -8, right, which is very tiny, around 16 nanosecond, right, which is very short time, and then returns to its ground state, right? The resonant state is like a exciting state. Okay, you may have ever heard that before, the excited state. Find the uncertainty in energy at the resonance level, right? So we have to consider this expression, right? The product between delta E and delta T, and the quantity they want to know, delta E, they want to know is the delta E, right? So we have to move the delta T, which is this quantity delta T here, to the right hand side. So delta T will appear as the denominator, right? h/2 or h by 4 pi. So delta E is gonna be here as we move it to the right hand side. Okay, let's draw something. Yes, the sodium atom, right? You have sodium atom, and of course there is nucleus, proton, neutron, blah blah blah, right? And there will be electron. No, they don't talk about the neutron at all, the electron at all. So they just want to observe the vibration of the whole atom of the sodium, and the observation time is the 1.6 times 10 to -8 second, and then it after the vibration, right? There's the atom of sodium remains the ground state, so there is no vibration. Find the uncertainty in energy at the resonance level. So we're gonna use this expression, right? Yeah, delta E, once we move delta T to the right hand side, is gonna be h by 4 pi, right? And times delta T, right? So once we substitute 6.626, right? It's 626 times 10 times, oh no, 6 before, 626 times 10 to -34 and 2 seconds, right? And you divide it by 4 pi, and delta T, the observation time there, it's 1.6 times 10 to -8 and second, right? And you know that at the denominator you have the unit of second, and you have second at the numerator, so it's gonna both will cancel each other, and you get only the unit of joule, right? That's the unit for the energy. Okay. Yeah. Once you put it into the calculator, put them into the calculator, you will have the result like this, right? In equation 75, which is in the SI scale, it's 3.29 and 6 times 10 to negative 27 joule, right? And yeah, you may see that the unit here, which is in the standard international system, is not appropriate, right? It's too tiny, 27, right? So it's better if you convert it to the EV, right? So it's going to be 1.6 times 10 to negative 19, right? It's electron volt per, oh, sorry. It's joule. This is joule per electron volt, right? And yes, you would get, after you put it into the calculator, you will have 2.057 times 10 to negative 8 and EV, right? Electron volt, and that's the more appropriate scale for the energy in the atomic level. So that will be our destination. Okay. Yeah, you have already seen the application of the Wien-Heisenberg uncertainty in terms of energy and time, right? We have not only the uncertainty along the x-axis, x scale, but also the uncertainty of the product of energy and time. So let's move to the next thing. Yeah. Well, in the book number 2, they say delta P is greater than h by 2 pi. And I found that it's not consistent to other reference. Okay, and for the uncertainty in terms of energy and time, it's also represented by h by 2 pi. It's only one h slash, it's not the case, because once we browse it more reference, it's going to be only half the h slash. Okay, half the h slash. Okay, now we move to another topic, which is called quantum mechanics. Okay, the Bohr theory has already addressed this before, right? We have already seen the Bohr atomic model. Okay, the allowed energy levels depend only on the principal quantum number n, right? Whatever situation you saw previously is something depending on the quantum number in even this one, okay, En and lambda, or even the radius of the atom, right? In terms of Bohr model. But once there was progress, there was development in theoretical atomic model, physicists have found something, okay, and the idea of only a single principal quantum number may not be appropriate. And then they found that there are two more quantum numbers. The first one is orbital quantum number, which is denoted by L. Okay, so something more complicated will emerge to us right now. Okay, yeah. orbital magnetic quantum number is the third one. Okay, this is the first one, n, right? The small n is the principal quantum number, and the next one is orbital quantum number, which is denoted by L. The third one is orbital magnetic quantum number, is denoted by ML, and L will depend on n, and M with the subscript L will depend also on L, right? But that's not all. Those are not all the quantum numbers that we are going to have. Okay, there is still one missing quantum number you're going to see that, but actually you have already seen that the last quantum number, or the fourth quantum number in the theoretical or standard table of elementary particles. Okay, in this table, you have already seen that quantum number in this table. Oh no, where is that? Here in this table, right? What is that? What number you have seen? What number have you seen in this? Did you see in this table? There was a number that we have considered in this table, right? Yeah, that's the fourth or the last quantum number. Okay, anyway, let's see the relationship between the orbital quantum number L to the principal quantum number N, and the orbital magnetic quantum number ML related to in relation to principal quantum number N. Okay, or to L again before, right? Okay, N could be any number, any integer from number 1, number 2 until the last one, which is infinity. And L is could start from 0, 1, 2, 3 until the maximum number N, right? In minus 1, okay, subtracted by 1. For example, if N is 5, L can be 0, 1, 2, 3, 4. Okay, not 5. 5 is the maximum, which is the maximum, the value of N. And when L is already known, right? From, for example, when N is 5, this one is from 0 to number 4, and ML is going to be is generated again from this L, right? For example, if L is 1, this one could be minus 1, 0, and 1. Okay, could you understand it? For example, okay, let me write down. If N equal 5, oh, it's too big, too much. I'm sorry. Let's say when N is 2, L could be a number in the set between from 0, 1, oh, and that's it. Nothing more, right? When N minus 1 is 1, right? And then ML is the number between sorry. When L, okay, there are two cases. When L is 0, ML could be only 0. Okay, it means ML will be only 0. There is nothing more. Okay, but when L is number 1, ML can take several values. It's what is that? Minus 1, 0, and 1. Okay, you understand that? That's the case for N equal to 2. Okay, the principal quantum number equal to 2. So you have this situation. But When n is greater than number 2, you're going to have more complicated situation for L and ML. All right. One may notice that the number of allowed state for n is infinite. Okay, it can be infinity. The number of allowed state for L is n. Okay, you can say that when n is 2, the number of elements in this set is also 2, right? When n is 3, you have L in the set of 0, 1, 2, but the number of elements is 3. The number of allowed state for ML is 2L plus 1, right? 2L plus 1. For example, you have n equal to when L is 0, and this one is 0, right? 2 times 0 is 0, so plus 1 is going to remain 1. That's why you have ML equal to 0, which is only a single possibility. But for L equal to 2, when you substitute L here to be 2, you're going to have 2 times 1 plus 1, that's equal to 3. So you could see that there are 3 elements in this set, right? That's the meaning of this counting procedure. Okay, let's go to the first few examples of first few cases for n, right? For when n is equal to 2, when n equals when n equals 1, you have only yes, n 1 minus 1 is 0, right? You have L equal to 0, and ML equal to 0 and 2, right? Because when your L is 0, you have only single possibility, which is number 0. When n equal to 2, L equals 0 and 1, right? ML is 0. This is the case for L equal to 0. ML could be minus 1, 0, and 1 for L equal to 1. And that's the case. N equal to 3, you could have L from 0 to 0, 1 to 2, right? And that's the same thing for L equal to 0. The possible value for ML is only 0. And you just copy this, okay? When L is 1, you could have ML from minus 1, 0, and 1. But when L is 2, you could have minus 2, minus 1, 0, 1, 2. Okay. And that's the thing. The possibilities of L and ML is going to be larger and larger. You could see here when n equal to 4, you could have L from 0, 1 to 3. And yeah, we span L0, L1, L equal to 1, L equal to 2, L equal to 3 to these 4 cases. Yeah, the first 2 cases could be copied from the former n equal to 3. But this one, once you have L equal to 3, the possible set of ML will be minus 3, minus 2, spanning until number 3. Okay, and you could see that here that the number of possible values for the elements inside ML set is 7, right? Because according to this rule, once you have L equal to 3, 2 times 3 will be 6, and once we add it by number 1, we get 7. So there will be 7 values possible for ML. Okay, and you could see you could extend this idea further to the case when n equal to 5. Okay, it's not difficult because we are not in the realistic in the actual room, right? So I could not actually, we are in the online classroom. Anyway, let's go further. Maybe you have ever seen this counting system. Maybe you have seen in the subject of chemistry, but in physics, you know that n could be any integer, right? 1, 2, 3, 4, 5 until 6, and L could start from any value which is less than n, right? Which is n equal to n minus 1, and the shell symbol. Shell symbol is the capital English alphabet. Okay, that is, those are that are in agreement. Okay, in for several researchers in this society. Okay, they use the capital K to represent n equal to 1. They use the capital L to represent n equal to 2. They use capital M to represent n equal to 3. Okay, and so on. Okay, M, N, N, O, P. Okay, if they say K, okay, you need to realize yourself that it means n equal to 1. Okay, and when they say the shell symbol as the capital N, it means you need to remind yourself that n, the small n, is equal to 4. Okay, and so on. Okay, that's the standard letter used to denote several values for n. And for L, right? L could be any value, right, less than n. L is also integer. It's a positive integer. It's not negative, right? But ML could be negative, right? For L, if they say small s, okay, small s represent L equal to 0. When they say P, it means that our L is equal to 1. Okay, S, P, D, F, G, H. I don't know the reason why they use the alphabet, why they don't use the alphabet in order, right? It should be A, B, C, D, E, F, G, H. I don't know. They just simply use S and P, D, F, G, H. Okay. For the shell symbol, you could observe that these letters are in a good order, right? K, M, L, M, N, O, P. But for the subshell symbol, which is in the small font, S, P, D, F, G, H, are not in the appropriate order at all. Okay, we need to remember in our brain. But if you work in this society quite a lot, okay, you may remember automatically. Okay, for L equal to 3, we have the subshell symbol F. For L equal to 4, you have the subshell symbol G. For L equal to 5, we have subshell as the letter H. Okay, shell and subshell notation borrowed from the book number 1. Okay, this is in the standard form. And one more thing is that you may already see that not only the principal quantum number n we have, okay, there are also 2 more quantum numbers. The second one is orbital quantum number L, right, and the orbital magnetic quantum number ML. But once we reach a certain state of theoretical physics experiments, a group of researchers have found this experiment. Okay, we will see the detail. The energy of electron is slightly modified when the atom is immersed in a magnetic field. Okay, so this is the low magnetic field, and that's the value the physicists could calculate from the Bohr expression, right? Minus 13.6 divided by n square, blah, blah, blah. Okay, but for the medium magnetic field, the energy levels from the single energy level, we have a split levels for the energy. It's and why how could the physicists observe the splitting energies for the electron orbits. They observe this phenomenon from the light bar. Okay, here if we have a single level of the electron energy, we have only a single bar of the light. Okay, the yellow light. But once the physicists introduce the electric magnetic field to that atom, the energy level of the electrons, possible energy of electrons, are separated into levels like this. Okay, this is the medium amount of magnetic field. You could see 2 bars of yellow, and once you increase the magnetic field strength, the difference of these energy levels will be more far from each other. And what you could observe in reality is the wavelength of these 2 yellow lights are more far away from each other too, right? And that's the meaning the energies of these electron orbital are far from each other. Okay. Yeah, at this experiment, physicists got trouble. So what is the reason behind this, right? Once they found this experiment, this phenomenon, this effect is known as Zeeman. Okay, Zeeman effect is the splitting of energy levels of atoms and molecules upon the presence of magnetic field. Okay, once we introduce magnetic field to the atom, right, we could see the split of energy levels like this. Okay, and yeah, or from another source, from another book, once we have the atom without any magnetic field, you could see the energy level as A. Okay, in this area, which is only a single energy level A. And once we introduce the magnetic field, so we could see several energy levels in the area B. Okay, and yeah, for another experiment, yellow light from a sodium lamp, right? They use the yellow light from the sodium lamp they use this light to demonstrate the splitting of the emission lines of atomic spectra. Okay, yeah. Once we leave the magnetic field, we could see the energy level splitting from each other in the difference of the wavelength here that appear on the chart is 0.97 nanometer, and the energy level difference is 0.0021 energy electron volt, right? And it's denoted by 3p in 3p 1 by 2 3p 3 by 2. What is the meaning of 3p? P means L equal to 1, right? Yeah, we see 3p equal to 1, and when n is 3, we're going to see number 3 in front of that. Okay, and that's the meaning of the splitting energy levels in yeah. This might correspond to minus 3.04 in yeah. The light, this is in EV, right? In the difference between these 2 layers is the 0.0021 electron volt, and for the again when 3, right, when n equal to 3, and we have here S, right? S mean S mean L equal to 0, right? L equal to 0, and 1/2 is the spatial number. Okay, we will talk about it later. This is the way how we get the yellow lights when the energy is when the electron fall from this energy level to 3s level, and from 3p, which is the lower one, to the 3s level on the same energy level. By using high resolution spectrometers, okay, it's a spatial device to detect this difference. Okay, it's not simple. You have to use a spatial measurement device. It is found that the lamp using sodium vapor, okay, it's the gas state of the sodium. Inside the bulk of that lamp exhibit two close yellow frequency, this one, right? And two yellow frequency are different by far away by this amount of wavelength, right? 589.0 and 586 nanometer. So it's the difference of the wavelength is only 0.6 nanometer, but they are different. Okay, they are not from the same energy level, and you need to use a high precision spectrometer to observe the light from these two layers. Okay, it's beyond the scope or the ability of our human eyes to detect this the difference of wavelength from the yellow light. By using high resolution spectrometers, we found that the yellow light emits two wavelengths. The first one 589, this one, and 589.6, okay, a little bit greater, okay, this one, right? Yes, the larger the wavelength, the lower the energy, right? So the energy difference here is smaller than this one, right? The two distinct frequencies are known as phi structure, but no one could give any explanation to this phenomenon. So what is the reason behind that? No one could tell. So yeah, and that's the challenge to many physicists at that time. Okay, the idea of electron spin, okay, was widely accepted as that suggested by Georg Uhlenbeck and Samuel Goudsmit. But it was actually proposed by Leif Kronich during his PhD in January 1925 at Columbia University. Okay, if you want to discover something which is which has high impact to the world, right? You may need to study PhD to do the doctoral degree, right? And only at the PhD level, okay, you could build up or discover something meaningful to the world, okay, the world of science. And that's the Leif Kronich, okay, PhD thesis that addresses the idea of electron spin, but no one would accept it at that time. Okay, only the people that have influence to the society, like Professor Georg Uhlenbeck and Samuel Goudsmit. This effect was well explained or completely explained by an Austrian physicist whose name is Wolfgang Pauli. Okay, this guy is quite important to the Society of Physics, and if you want to see who's this person, right? Wolfgang Pauli. Wolfgang Pauli, right? This guy is quite meaningful to us in atomic in quantum mechanics. Oh no, this is in German. Here. Okay, this is Wolfgang Pauli, but his full name is actually Wolfgang Ernst Pauli. Okay, he's the German, and he was, or this is the German word, and he's an Austrian theoretical physicist. I mean, he's from Austria, and he is the pioneer of quantum physics. Okay, and he also received the Nobel Prize. Okay, because he discovered or gave the good explanation of the electron spin, but the idea was actually discussed by Laf Kronig, but he is not well accepted because at that time he was only a PhD student. To describe atomic energy levels, Wolfgang Pauli proposed a fourth quantum number. Okay, yeah, and that quantum number is known here. Okay, you may have already seen in the standard table of elementary particles in physics. It's called a spin number. Okay, spin number could be 1/2 or negative 1/2, right? The spin number. Where is that? Yeah, we'll talk about it later. Yeah, the spin number is the last quantum number that physicists have accepted. Okay, maybe in the future there might be another new quantum number. I don't know. Okay, but at the moment there are only 4 quantum numbers. Then the last one, which was just discovered on Earth, is the spin number. Okay, this effect was explained by Wolfgang Pauli. To describe the difference of the splitting of the energy levels here. Okay, this fourth quantum number is called spin magnetic quantum number, or simply speaking, spin number. Okay, the full name is spin magnetic quantum number. What is the difference then? The second and the third orbital quantum number, right? It's called yeah. The second one is called orbital quantum number, and it is denoted by the letter L. And the third one is the orbital magnetic quantum number, M with the subscript L. And the last one is called spin. I need to mention again here. Okay, orbital quantum number L and orbital magnetic quantum number M with subscript L. And the fourth or the last one is spin magnetic quantum number M with subscript S. Okay, M with subscript S here. And simply speaking, we call spin number MS. Okay, the spin number MS is not only any feature in the solution of the Schrodinger's wave equation. Okay, if you go into the detail of the theory of quantum mechanics, physics would start from Schrodinger's wave equation. You may see some in the next section. You could not find the detail of spin number MS in the Schrodinger's wave equation, but it comes from the equation derived by Paul Dirac in 1927. Okay, because we are in the high school level, we could not get into the detail of many things on this. Okay, because it involves a lot of calculus. Okay. Anyway, for us in the high school level, what we could understand is the following. It seems like this is the nucleus of the atom, right? It composed of proton, neutrons. Okay, several number. It depends on how big your element is, right? In the electron is moving in this way, okay, around the nucleus of the atom, and this is the electron, right? Denote E with superscript minus, and the electron, let's say it turns around like this by using the right-hand rule. Your time direction is going to point up, and we would call, if the electron during this rotation, we would realize that it seems like electron rotate itself. It's like our Earth rotates itself, right? That's why we have daytime and nighttime. But anyway, our Earth just move around the sun, right? Which is the center of the solar system. It's something like that. For the atom, we have nucleus, and electron is moving around the nucleus, but at the same time, it seems like electron is rotating around itself, but it's not true at all. Okay, the physicists just give this notation. It looks like, okay, the electron moving around itself, but it's not true at all. Okay, yeah, if the electron is rotating around itself, and the movement in this direction, according to the right-hand rule, we would have the time direction pointing up, and in this manner, the physicists call spin up. Okay, and spin up will correspond to the value of ms equal to 1/2. Okay, and that's why we have here the notation for the here the ms equal to 1/2. Okay, 1/2 for the up quark, down quark, and so on. Even the electron has the 1/2 spin number, and many elementary particles have also the spin number as 1/2. Okay, and photon has spin number as 1. Higgs boson has no spin number at all, and so on, right? Yeah, 1/2 is the spin up quantum number, and it is also possible when the electron moving around itself, and it moves in this way. If you look from the top view, you look at it from top view, is like a clockwise direction, right? And the clockwise direction will lead to the thumb finger pointing down, and this it's known as spin down. Okay, and when the electron seems to rotate like this, okay, in the clockwise direction or the thumb direction pointing down, you have ms equal to 1 or minus 1/2, and that's the spin down electron. Okay, and the energy of the electron is slightly different for the two spin direction. Okay, during the rotation around the nucleus, electron could have two possibilities: spin up and spin down movement. And with these two difference of spin up spin convention, we have two levels of energy right here: 3/2, 3p 1/2, not 3pi, sorry, 3p. Okay, ms equal to 1/2, meaning spinning up. Ms equal to minus 1/2, meaning spinning down. Okay, the energy of the electron is slightly different for the two spin direction. Okay, so yeah, the meaning of slight difference means the split of these two energy levels right here. Okay, and yes, the energy difference account for the sodium doublet or double energy levels, sodium double waves. This new quantum number doubles the number of allowed state from the conventional quantum state in the literature that are previously specified by 3 quantum numbers such as n, okay, the principal quantum number, L, the orbital quantum number, and ML, the orbital magnetic quantum number. Okay, so right now at the moment we have 4 quantum numbers, right? So we need to reach 1410, right? Not sure it's 1410, 605, 1410, right? 1420, I'm sorry. So at 14 we're gonna finish and we let M604 to get into the classroom. Okay, let's continue our story, the quantum mechanics. Let's consider a hydrogen atom. Now we will get into the detail of the configuration of the quantum numbers. Okay, now the quantum numbers are plural. Okay, not only a single number anymore. Determine the quantum. Let's consider the hydrogen atom, right, which is the basic atom for us. Determine the number of states with a unique set of values for Lm, Lms for n equal to 2. Okay, once you have n equal to 2, right? Once you have n equal to 2, yes, L could be, what is that? L could be 3 possible cases, right? The first one, L equal to 0. Oh no, 2 cases only, MSTB. There will be only 2 cases, right? Because L equal to 0 and L equal to 1, right? Yeah, for L equal to 0, you could have ML equal to 0 only, and here you have ML equal to any value in that set between what is that? It's -1, 0, and 1, right? Yeah, something like that. And MS is the possible value for the new quantum number, which is spin number, right? MS could be 2 things, 1/2 and -1/2, right? Yes, and this also valid for the case here. So you could have 1/2 and -1/2. All right. Yes. So now it's time to make the configuration of quantum numbers. So you would have a set of N, L, M, L, and MS, right? N could be 2, right? So you have 2, L is 0, M could be 0, and MS is 1/2. And another possible case is 2, 0, 0, -1/2. Okay, and anything else? Nothing more, right? But for the right hand side, once we draw it here, we could have n equal to 2, right? N equal to 2, and L is number 1, ML is -1, and you would have 1/2 for the first case. You have 2 for N, you have 1 for L, and ML, oh, sorry. ML is -1, and here the spin number is -1/2. Okay, and the next one is 2. Once the L is 1, right? So we have 0, and because L moved from -1 to 0 already. So this is the case. All right. So ML is 0 right here, and the spin number could be 1/2. For the first case, you have 2, 1, 0, and -1/2 for the second case. Okay, and because of the short, because we are running out of space, let's write down here. The next state is 2, 1, and now we move ML from 0 to number 1. So that's why we have here 1. And again, spin number could start from 1/2. And then second case is L is number 1 in MS is number 1. The spin number is -1/2. And that's all of the possibilities to the spin number configuration, right? You could have 1, 2, 3, 4, 5, 6, 7, 8 cases. Okay, for the quantum possible quantum state or possible values of quantum numbers. So that's so here in total we can have 8 quantum states like this. Okay, this is the spanning of the possible value for NL, ML, and MS, and that's the quantum state, possible quantum state for n equal to 2. Okay, for the homework, you can choose any n to get another type of quantum states. Okay, here, let's consider a hydrogen atom. Determine the number of states with a unique set of value for L, ML, MS when n equal to 3. Okay, when n equal to 3, what is the possible quantum state to this case then? Right? What is the possible quantum number to this case? Let me turn on the lamp. I forget to close the lamp, otherwise there will be reflection from that monitor. Okay, right here you could have the quantum state like this. Okay, and for n equal to 3, let's go ahead with that. Okay, when n equal to 3, you could start like this. Okay, when n equal to 3, there will be 3 cases for L, right? L equal to 0, that's the first case. L equal to 1, that's the second case, and L equal to 2 as the third case, right? And again, ML could be minus L, 0 in L, right? So right here you could have only 0 value for ML, and right here you could have ML equal to ML equal to -1, right? And ML equal to 0, and ML equal to number 1. And here you have ML equal to -2. You have ML equal to -1. You have ML equal to 0. You have ML equal to number 1. You have ML equal to number 2. Okay, and that's the 5 cases, 5 possibilities for L equal to 2. Okay, and once you know the configuration like this, it's the case for MS, right? MS could be 1/2. MS could be -1/2. And again, here, MS could be -1/2. Oh, sorry, positive first. S is 1/2. So MS could be again minus 1 by 2. And here you have ms equal to 1 by 2, ms equal to minus 1 by 2. All right, ms equal to 1 by 2, ms equal to minus 1 by 2. All right, the whole cases, the whole thing here, ms equal to 1 by 2, ms equal to minus 1 by 2, ms equal to 1 by 2, ms equal to minus 1 by 2, ms equal to 1 by 2, ms equal to minus 1 by 2, ms equal to 1 by 2, ms equal to minus 1 by 2, ms equals 1 by 2, ms equal to minus 1 by 2. Okay, so let's count the possibilities to this n equal to 3 case. This is the sorry, let's use this one. The first case, the second case, the third case, the fourth case, the fifth case, the sixth case, and the seventh case, the eighth case. And here we have the number 9 case, the number 10 case, number 11 case, and the 12th case, the 13th case, the 14th case, the 15th case, the 16th case, the 17th case, the 18th, the last one. Okay, so the number of state, okay, therefore the number of possible states is, what is that? It's 18. Okay, it's 18. We have 18 possible states for the electron orbits. Okay, in yeah. Let's move to the next example, next detail, right, to this lecture. The question is the electron spin realistic? Is that true? All right. Is that correct? Okay, and that's the question to this one, right? Yes. Let's consider the spinning speed of the electron, right? Spinning speed. Okay, you just take a look at the ball. If this is the sphere, right? If we represent the electron by this sphere, it's like, it looks like a ball. Okay, a football, basketball, or any type of spherical ball. And let's consider the spinning speed of the electron, which is actually the tangential speed. Okay, any rotating object that rotates around itself, this is the tangential speed, right? The speed at the surface of that ball or that object, right? Which could have the, okay, this assume we have the rotational speed, which is omega t. The rotational speed is omega, or no, not omega t, I'm sorry for that. Only omega, that's the, I don't know, angular velocity. Yeah, and the radius, let's say the radius of the electron. Oh, sorry for that. Let's say the radius of the electron is RE. Okay, RE. So the tangential speed could be found from the product or the multiplication of the angular speed times the radius of this electron, right? So you could get the tangential speed tangential speed from this expression. Okay, then we are going to see the tangential speed of this electron. Okay, that's the basic formula from the classical physics, right? Let's recall the moment of the inertia of a sphere. Okay, if you get back to material 4, material 5, you have ever heard this one, right? The moment of inertia of any geometrical shape. For example, we consider the sphere right here, which could be found from I sphere equal to 2/5 and mr square. Okay, and let's say if m is the mass of any object, and we are considering here the electron, so the mass should be the mass of electron, and the radius of this thing should be the radius of the electron. Okay, and this is the general form or general expression for any shape of the object. Okay, and we are considering here the sphere, right, which represent electron. Okay, it's a kind of lepton. Okay, it is well known that the angular momentum of any object is the product of moment inertia and the angular velocity. So once you multiply this term to omega, okay, 2/5 mr square to omega, you could get the angular momentum, and the angular momentum is h/by2. You have the h/, and once you solve this term, okay, for omega is omega t/re, you put you leave vt/re to the position. When you substitute vt/re to omega, you would get the value for vt, and the tangential speed of the electron here. Okay, if let's say if you are very, very small and you just stand up at the surface of the electron, you're gonna feel the speed, right, that try to move you. It's 5/4 h/by me and re. Okay, you substitute everything, the h/ in this is the max Planck constant divided by 2π, right, the angular version. In the mass of electron is 9.1 10 to -31, and radius of the electron is 2.82 10 to -15. Okay, even less than the atomic size. Okay, atomic size is on the order of 10 to -10, right? It's 1 angstrom, but this one is something less than, much less than 1 angstrom, 10 to -15. That's the radius of electron. Okay, and once you move everything, you substitute everything to this expression and you leave it into the calculator, you're gonna get the speed, right, the tangential speed at the surface of the electron. If you stand up here at the surface of the electron, you would get the speed vt. Okay, and the outcome is the following: the speed of the tangential speed at the surface of the electron is emerged as 515 10 to 8. Okay, and you could see 10 to 8 is the same scale as the speed of the light, right? The light or any electromagnetic wave move from the Hertz-Heilig-Hertz formula 3 times 10 to 8, right? That's the speed of the light or any kind of electromagnetic wave. An important note is that the electron doesn't physically spin, whereas this electron spin is a pure quantum effect that gives the electron an angular momentum as if it were physically spinning. Okay, because 513 is much greater than number 3, right? We usually know that the speed of the light is 3 times 10 to 8, right? So it's not the case here. It's much greater than the speed of the light, and any object could not move faster than the light. So 513 is not a valid value, but we could we could get it from the derivation or from the theory, but it doesn't hold true at all, because this value is more than the speed of the light. So any object in the universe could not have the speed much greater than the light. So this doesn't hold true. This is not valid. This is invalid. So it means that the electron doesn't actually rotate around itself. Okay, this notation, this understanding is not correct at all. But what is the reason why they say the electron try to rotate itself according to this figure? According to this figure, okay, here spin up and spin down. So in reality, the electron doesn't rotate around itself. Okay, this is only the pseudo configuration. Actually, the electron doesn't rotate around itself, whether spinning up or whether spinning down. The electron doesn't physically spin. Electron spin is a pure quantum effect that gives the electron an angular momentum as if it were physically spinning. Spin is an intrinsic or the hidden form of the angular momentum, but actually the electron doesn't spin and doesn't rotate at all. The Pauli exclusion principle states that no two electrons in an atom can ever have the same set of values of the set of the quantum number in LML and MS. So what we have distributed here, the possibility like this one, okay. The set of these four numbers here is the unique location for electron, okay. Electron, the electron which are more than two, okay, more than two electrons cannot have the same set of quantum numbers here, okay, and that's called Pauli exclusion principle, okay. Pauli proposed the idea of exclusion principle. So electron could not have the same set of quantum number like this, like what we have distributed here for n equal to 3, or this one for n equal to 2, okay. And the lecture for at the moment, okay, it should be finished right now. And M605 can leave the lecture right now because I have to leave you 20 minutes for the break, right? And see you in 50 minutes, right? You get to another subject, which is English or something like that. And we will see each other again, okay, in 50 minutes. สวัสดีครับ bye bye ครับ If you have any questions, just let me know. If not, then just take the break. Bye bye ครับ เดี๋ยวพบกันอีก50 นาทีนะครับ 1410. Yes, it's this one. $14.20. Okay, no test 1, 2, 3. Test 1, 2, 3. Okay, so it's time for the session of M604, right? อาจารย์ณัฐพลของคุณนะครับผมลืมบอกห้อง605ไปด้วยเขาประสบอุบัติเหตุนะครับก็นะครับเขามีการแจ้งกันตั้งแต่เมื่อคืนนะครับให้ผมมาแทนครับไม่ใช่แบบว่าผมอยู่ดีขอเขามานะครับคือจริงผมติดธุระด้วยนะครับเนี่ยแต่ว่าก็ไม่เป็นไรครับเขาให้มาแทนนะครับเนื่องจากอาจารย์ผู้ที่รับผิดชอบวิชาค33252นะครับของคุณนะครับของ M604 นะครับเขาประสบอุบัติเหตุครับก็เลยให้ผมมาแทนครับผมก็ไม่รู้ว่าเขาจะกลับมาได้เมื่อไหร่ครับก็ดูเพิ่งเกิดเมื่อวานนี้นะครับก็ต้องขอแสดงความเสียใจด้วยนะครับก็ผมก็คงต้องปฏิบัติหน้าที่แทนเขาไปก่อนครับแล้วเขาคงจะมาขอใช้ชั่วโมงคืนเมื่อใดก็ตามนะครับก็โอเค so let's continue our lecture right now. You have ever seen the Werner-Heisenberg uncertainty principle, right? In terms of the coordinate along the x-axis, which is the delta x, and the coordinate as the the uncertainty of the momentum, right, along the x-axis, which is denoted by delta px, right? And the product of those two terms, two quantities, is not less than, right? Or simply speaking, it's always greater than or equal to h by 4 pi. And then h/ by 2, right? It's h by 4 pi is the main thing. It's half the h/, which is the angular Max Planck constant. Okay, angular version of the Max Planck constant. That's what we have considered in 65, right? But here in at the moment we arrive at the another version, another configuration for the Werner-Heisenberg. Okay, not only the location and the momentum along the x-axis, it actually involves the speed along the x-axis, but also the energy and the time. Okay, the Werner-Heisenberg uncertainty also involves the energy and the time, and the detail is the following: the product of the uncertainty of the energy, which is denoted by delta E, this variable, and the uncertainty of time. Okay, the period of time which is not sure. Okay, which is in doubt. Okay, the product of these two terms is again similar to 65. It's greater than or equal to h by 4 pi. Okay, it's not less than half the h/, okay, the angular version of the Max Planck constant. Okay, that's the whole thing here. the energy here is in the SI scale, which is in Joule, and time is in second, and you know the maximum constant is in Joule second, right? Yeah. Delta E is the uncertainty of the energy in a particular state. Delta T is the time interval of the system that stay in that state. Okay. Yeah, it depends on what you will apply to. Okay. It's valid to many cases, many situations. Okay. You can use this term to many situations, and I don't understand why we have a black a square box in this lecture, in this YouTube channel. I don't know why. Okay. Here is the first example. In order to completely understand what's going on with equation 73, we have to consider this example, which is taken from the book number 2, example 28.11, okay, 28.11. We consider the sodium atom, and it doesn't go into the detail of electron or any structure. Okay, let's say this is atom of sodium. Okay, sodium is an element in the periodic table, right? Sodium atom stay in a resonance state for an average time of 1.6 times 10 to negative 8 seconds, and then it returns to its ground state. What is the resonance state? It means the state that has high energy, and once the energy is completely released, okay, the energy in the whole system of the sodium atom reduces, and the atom returns to its ground state, and that's the whole thing here. The time of observation is this one. Okay, here, right? That's the amount of time of its observation time, and delta E will be what they want to know in this example. Find the uncertainty in energy at the resonance level, right here. Okay, yeah. So they want to know delta E at the moment. Okay. Yes. We can apply this formula, which is the second case of the Van Heisenberg uncertainty. This one is the uncertainty along the x-axis. This is the uncertainty related to the energy and time. All right. So let's open the next page. Okay, like this. Delta E is what they want to know, right? And delta T is the time of observation they have provided. Well, it's 1.6 times 10 to negative 8. The unit is already in the SI system second, right? In once we want to know delta E, we have to move the second term delta T to the right hand side. So delta E will be oh no, not equal to, I'm stupid, will be greater than, okay, not less than this. Okay, the precision is not less than this. Okay, the uncertainty of the energy is greater than or equal to h by 4 pi, right? And once we move delta T to be here, we're gonna have we will have delta T also appearing here, and that's equal to 6 times 6 times 10 to negative 34 divided by 4 pi delta t is 1.6 times 10 to negative 8. And this is joule second, right? Joule second. And this is in second, right? That's the observation time in the SI system, standard unit system. Yeah, the crossing parenthesis too. And once you look at this ratio, you're going to see that the unit of second appear at both numerator and the denominator. So it's going to cancel. Both will cancel each other. The remaining unit will be only joule, right? Which is the unit of the energy on the left-hand side. So let's get into the detail. Once you substitute it into the calculator, you would get the result in terms of SI system. SI system like this, 3.29 5 times 10 to negative 27 joule. All right, and oh, sorry for that. My God. But it's not appropriate, right? Because 10 to negative 27 is quite far from human perceptibility. Human perceptibility. So yeah, it's better if we convert it to the better unit scale. So, and that scale is the electron volt, right? We just divide this amount by the charge of electron, right? The charge value of the electron. So it's better if we divide this by 1.6 times 10 to negative 19, right? And the unit for the conversion is actually EV, right? EV per joule, right? Which is the charge of of any charge value for any object, right? So once we, oh, sorry, it's joule per EV. It's this value joule per EV. Yes, there is something like that. And once you put it into the calculator, you would get 2.057 times 10 to negative 8, okay, EV. So 10 to negative 8 is closer to what we could realize, right? It's like a 20.57 nano electron volt. So that's the minimum energy uncertainty we could observe from this system. Okay, and here's one of the example that we could apply the Van-Heisenberg uncertainty, okay, which is related to the energy and time. All right, so that's the whole thing for the Bohr model, right? The whole thing for the whole Bohr model. One important thing we have to notice is that if you have some time and you go through the book number 2, the reference number 2, in equation 22 and equation 23 in the chapter 28, you would find that the Van-Heisenberg uncertainty is denoted by h by 2 pi. It is not correct, because once we compare this term to many other references, it's not correct. it should be h by 4 pi, which is what we have here, okay, in this lecture. So I have done the mistake before, okay, in the last year, but so to prevent the mistake with you again this year, I have to mention that please don't use this formula. It's not correct. H by 2 pi, okay. H by 4 pi is the correct one. Okay, yes. And now we move to the next topic, which is quantum mechanics. Okay, quantum mechanics is the story about quantum states. Okay, you know that quantum state is the possible orbit, the possible location that the electron could locate. Okay, could locate. It means in that layer, electron could turn around the nucleus and can move around the nucleus of that atom. The nucleus consisting of proton and neutron, right? Okay, let's make conclusion. In both theory, the allowed energy levels depend only on the principal quantum number n. Okay, only the number n. There are two more quantum numbers, such as orbital quantum number L and orbital magnetic quantum number ML. So these are two more quantum numbers that the physicists have the physicists discovered in the past. Okay, L is the sub level of the energy apart from the main energy level N. Okay, and orbital magnetic quantum number is the sub state from the quantum orbital quantum number L again. Okay, and all these two new numbers came from the Schrödinger's wave equation. Okay, we will not get into the detail of the Schrödinger wave equation because it's beyond the scope for you at the high school level, because in order to study the Schrödinger's wave equation, you need to have some skill in calculus. So once we assume that you in high school may not have enough skill in calculus, so we will not get into the Schrödinger's wave equation. Okay, you will see the complete view of the Schrödinger's wave equation. You get the whole expression Schrödinger's wave equation once you enter the university, or if you have your time, you can go to any source of books or website that talks about the expression of the Schrödinger's wave equation. Okay, but for us at the moment, we will see only some results in terms of quantum number, like orbital quantum number L and orbital magnetic quantum number ML from the Schrödinger's wave equation only. Okay, the allowed values of these quantum numbers are given by this equation 76. Okay, the first one is the principal quantum number n, right? Is denoted by small n. Sorry, n start from n is an integer. You know, integer is a countable number, right? Countable number start from number 1, right? So n is the energy state that you have seen before, right? It's energy state. But there are also some sub states in terms of L and ML. Okay, let's talk about the whole range of n from 1 to 3, 4, 5 until infinity. Okay, infinity means that you are totally far away from the nucleus of that atom, whether it's hydrogen, lithium, or whatever. Okay, or helium or whatever. The state of infinity means that you are very far. That energy state is extremely far from the nucleus of that atom. So that's why we have n equal to infinity. Okay, the greater the number, the farther the energy level, okay, from the nucleus. And that's the idea of principal quantum number, right? For the next one, the second one, which is derived from Schrodinger's wave equation. You cannot see the Schrodinger's wave equation at the moment, but you will see it later in the bachelor degree. Well, L is L can be taken from the number 0, 1 until n-1. Okay, you have to pick up n first, okay, the main number in quantum state, and after that you can get the value for L, and L may not have many values, not only a single value. Okay, if for example, if n is 1, you have only a single value for L, which is only 0, because n-1 is 0. The possible element for L is only the number 0. So there is only a single possible case for L in this scenario. For when your n is number 2, 2 minus 1 is 1, right? So there will be 2 possible cases for L for you in these scenarios. So L could be 0 and number 1, right? And ML is the next quantum number. Is known as orbital magnetic quantum number. L is the quantum number that could be negative. Okay, it's different from N and L. N is only a positive number, positive countable number. L is a number that could be also 0, but ML is different, and also the next quantum number. ML is different from N and L because it can be also negative value, right? For example, when your L is 0, of course, NL will be only 0, right? Only 0. So when your n is 1, ML could be -1, 0, and 1. Okay. When your L is 1, number 1 here, your ML will be -1, and the next from -1 is 0, and the next portion from 0 is number 1. So ML could be -1, 0, and 1. And that's M604 มีคนจะเข้าที่ซูมขออภัยครับมันไม่ค่อยมีคนอยากเข้านะผมก็เลยไม่ค่อยได้เข้ามาดูครับ What is the problem มีคนรับชูอะไรสักอย่างมีคนทักผมที่ไลน์ครับ Moment what is that รับซูมหน่อยครับอ๋อรับซูมโอเคใช้สิทธิ์ sorry for that โอเคใช้สิทธิ์นะครับใช้สิทธิ์เข้ามาที่ซูมนะครับขออภัยด้วยครับนบนะนบใช้สิทธิ์ครับโอเค now we continue our story. Okay, yeah, ML is different from N and L. Okay, ML could be a negative value. Okay, -1, 0, 1. And if your L is number 2, this one will be ML will be -2, -1, 0, 1, 2. All right. One may notice that the number of allowed state of for n is infinite. Okay, this is infinity case. The infinity case means that we are extremely far from the nucleus of the atom, right? And the allowed state for L, the number of allowed state for L is n. Okay, you just count here. If your n is 1, so this one will be 0, which is equal to number 1. When your n is 2, you could have possible case for L as 0 and 1. So the number of possible elements for L is 2, right? 0 and 1. Yeah, it's valid for also number 3. When you have number 3 here, L could be 0, 1, 2. So the possible 3 values for L is 0, 1, 2 is 3. Right. Let's consider the number of possible possible numbers of ML. So the amount of possible numbers of ML is 2L minus 1. For example, if your L is number 1, it's going to be -1, 0, and 1. So there are 3 possible elements for ML. So that's the case. That's why they say 2L plus 1. Okay, maybe you cannot completely understand all of these. We have to get into the example. Okay, here is another explanation page. For n equal to 1, you can take or pick up only L equals 0 and ML should be 0. So you have only a single quantum state for the case n equal to 1. For the case n equal to 2, you could have 2 possible values for L, and that's 0 and 1. ML equal to 0 and L equal to 0. That's the first case. Okay, yeah, you cannot have any value apart from 0 for ML because your L is already 0. But once your L increases by 1 step, which is number 1, ML could start from -L until blah 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 until L, right? Yeah, -1 is minus L is -1 here, -1 and 0 and 1. Okay, and that's the maximum value of ML in this case. So there are 3 possible values of ML right here. Okay, and when your n is equal to 3, there will be 3 values for L, which is 0, 1, 2. Okay, as they say, the number of allowed state for L is n. Okay, if you have 3, you will have 3 possible elements for L. Yeah, and you start from ML equals 0, as same as before, and when your L is 0, when your L is 1, there will be 3 cases for ML, -1, 0, 1. That's the same thing here for n equal to 2. But one additional case is when L equal to 2, to number 2 here, you could start from -2, -1, 0, 1, 2. Okay, it's bigger than this one. Okay, because you start from -2 and you stop or end up at the ML equal to 2 is bigger. So the number of elements here is 5, and that's why we say 2L plus 1, because our L is 2. You just substitute L into this, you get 2 times 2 as 4 plus 1 remaining 5. And you could have here the number of possible elements in this set as 5. Okay, yes, let's go further. Now it's even more complicated, but it's based on the previous cases. Okay, it's not too difficult to understand. When n is equal to 4, L could be, of course, 4 values, right? 0, 1, 2, 3. Okay, the maximum value is n minus 1, where 4 minus 1 is number 3, and that's the maximum value for L. When ML is 0, L is 0. When L is 0, ML will be 0. When L is 1, ML will be -1, 0, 1, like this. Okay, it's somehow like this. When L is 2, you could have ML as -2, right? This one, -2, -1, 0, 1, 2. And when your L is equal to 3, you could start from something bigger than this case, right? You could start from -3, -2, -1, 0, 1, 2, 3. So the number of possible cases here is 2L plus 1. Once you substitute L by 3 into this expression, 2 times 3 will be 6, and plus 1 will be 7, right? And that's why you have here 7 elements in this set. Okay, and here is the first 4 generation of the quantum number or quantum states that could take place for the electron to move around any nucleus of the atom and etc., etc. So
You could also write down here n equal to 5, n equal to 6, 7, blah, blah, blah. And it has no limit because n could n could reach infinity. Okay, n could reach infinity later. But one important thing in the society is that, okay, you start from the principle, the basic thing, right? You start from the N, L, and ML, but it's not only that. This is the actual theory. But for the people who really work in this stuff every day, like in the society of atomic model or in some special society of physics, they would use something different. Okay, they use a special language. They use English, but they use different notation to represent the case when n is equal to 1 and n is equal to 2. Okay, when n is equal to 1, they use simply the shell symbol as k. Okay, the principal number k. Okay, instead of n equal to 1. So how could I say? Okay, you know from the theory before that n equal to 1 is the first thing, right? But for the people in this society, they just simply say it's k. Okay, and once you see the capital K, it means n equal to 1. Okay, and when n equal to 2, the people in this physics society would use simply the capital L English alphabet. Okay, and so on. When n equal to 3, when n is equal to 3, they use the letter M, capital M. When n is equal to 4, they use the capital N. Okay, 5, capital O, 6, and capital P, and so on. Okay, the shell symbol is represented by capitalized letter. Okay, the big font of the English alphabet. And for L, which is the orbital quantum number, right? It's the minor quantum number apart from the principal quantum number n. It's L, and they use the letter small s for when L is equal to 0. They use P for L equal to 1. They use D for L equal to 2. They use F equal to 3. There is no order at all. Okay, you could see S, P, G, F, G, H. Is not in the typical order of English alphabet, right? It should be S, T, U, V, W, X, Y, Z, or Z, right? But it's not the case here. They use S, P, D, F, G, H. It's not the same as shell symbol. The shell symbol is represented by ordering English alphabet K, L, L, K, L, M, N, O, P. I don't know the reason why they use S, P, D, F, G, H. It's not my favor. This is the convention they use in the physics society. I have no force to regulate them to use anything else. Okay, what I can do is only to deliver the information to you. Okay, the student. Okay, now the time is over. We have to stop our lectures. Oh, no. You have 10 minutes, right? It's not 20 minutes. We will stop at 15:10, right? We will stop at 15:10. So you could have only 10 minutes of break. Okay, ใช้สิทธิ์พิมพ์มาในซูมนะครับใช้สิทธิ์รู้สึกเป็นคนเดียวนะครับที่จะอยู่เข้ามาที่ซูมนะครับก็ยินดีครับด้วยความยินดีนะครับผมก็จะไม่ค่อยได้ดูบ่อยนะครับใครอยากเข้ามาที่ซูมก็เชิญนะครับ alright 15 this is shy is it right? Okay, we will continue our story. Let me check the time again. It's 15:10, right? So we still have more 10 minutes. So moment. Okay, Yes, let's continue our story. Yeah, as you know, I didn't set up this configuration. Okay, SPDFGH is the convention created by physics. Okay, I'm not physics. I'm from the engineering branch, so I have no idea at all. They use the small letter, okay, to represent the subshell. Yes, sorry. Yes. Yes. But the shell symbol, the capital, the main one, okay, the main quantum number is denoted by the capital letters like this, KL, MNOP, okay? Once you see P, it means N equal to 6, all right, and further, okay? But this is the first 6 symbols that you mostly see it in the convention of electron orbits. Okay, and that's the first stage about quantum mechanics. They derived the Schrodinger's wave equation. They got the idea of principal quantum number N. They have the quantum number L. They have magnetic orbital or magnetic quantum number ML, which could be also positive. Okay, the first 3 quantum numbers are derived from Schrodinger's wave equation, but once the time goes by, okay, once the time went by, the physicists have done some experiments, and one of the experiments which is quite meaningful to everybody is this one. Okay, they use the sodium, you know the sodium, right? Yeah, they use the sodium, which is in the gas state, right? It's sodium. Is sodium in the gas state. It's vaporized, okay, and you live in a closed area like the bout, like the lamp, and so on. And yes, once you put the electric field, or you let the current flow inside that, and the energy is transferred to the vaporized sodium in the lamp. Okay, you could observe a certain light from that lamp, which is in yellow category. And what they have done in this experiment is in the following 3 cases. Okay, in the first case, they just leave low magnetic field to that atom, to that bulb, to the lamp. Okay, and what they could observe is only a single bar of yellow, single bar of wavelength, or single bar of frequency. Okay, they could observe only a single frequency of the yellow light from the bulb. Okay, they have about the lamp like this. They fill in sodium in the gas state, and they close this one. Okay, they pump out the air and so on, other stuff. There will be only sodium into this area, and they release the energy by means of electricity or electric field and so on. Once sodium has more and more energy, it's going to release the energy in terms of yellow light. Okay, and once you know the B field, right? B field is the magnetic field. Once they leave the magnetic field here, okay, B field, they leave the magnetic field into this lamp. Okay, from the low level, medium level, and high level, what they could observe is that when the magnetic field is stronger for a certain value, the energy here is split into 2 components. Why they say two components? Because they could observe two lights, two frequencies of the yellow light from this experiment. Once they increase the strength of the magnetic field, when B is the magnitude of the magnetic field B is greater, when the magnitude B is increased, okay, the energy just split into two levels, and that's why they say two bars, two frequency of the yellow light. Once they increase more the B field, the magnitude of the magnetic field, the energy is even more split into two layers like this. And yeah, the two bars here of the yellow light in the spectrum domain in the frequency axis is more separated from each other like this. Okay, it's more far away from each other, and that's the result from increased magnetic field here. Okay, and yeah, when external magnetic field are present and individual spectral light A, okay, this is the original one without any magnetic field, will be split into several lines like in B area, and that's the effect which is called Zeeman effect. Okay, and I don't know, Zeeman is the person who would observe first, who is the first person who observed this, who have done this experiment, and I don't know. Okay, and in another figure, in more detail, with the same experiment, you know, there is the energy level minus 3.04 eV, right? This is the unit of eV. This is minus 5.14. This is the unit of eV. Okay, you would have you would have energy level for the electron like 3p, and 3s, right? What is that? This is the case when n equal to 3. This is the case when n equal to 3. And S, what is that? S is the case when your L is 0. When your L is 0. Or P, what is that? When your L is equal to 1. Okay, when L is equal to 1. And that's the subshell symbol P. All right. 3/2 and 1/2 will be discussed later, but the time now is over. Yeah, we will stop this one. Okay, we will talk about that later next time. So if you have any question, just let me know. Okay, if you have any question about the Werner-Heisenberg uncertainty in terms of energy and time, or the principle the first step of the quantum mechanics in terms of principal quantum number, orbital quantum number, or orbital magnetic quantum number, ML, right? Just ask me. Okay, and then if you don't have any questions, so we will have to stop the section for M604 right now, and the section for M605 will get back at 15:10 โอเคก็604นะครับบ๊ายบายครับสวัสดีครับ Okay, now let's get back to the section of M605 again for today, right? 0.4.01, and it's gonna be considered as a separated version of M605. You have to type your name again. Please write down M605. Okay, วีรพัฒน์ใช่ไหมวีรพัฒน์ oh no เมธาสิทธิ์กิติพันธ์ 19, right? Once for those who are from M605, once again, like Kantapon, please. I'm not sure Kantapon is from M604, right? For M605, once you get back to the classroom, please write down your name. You start first with the M605, all right? So that it could be differentiated from the previous M604. นะครับ M6 ห้อง 605 นะครับถ้ากลับมาที่เซสชันนะครับถ้ากลับมาที่เซสชันได้โปรดนะครับพิมพ์605นำหมายเลขที่ของคุณนะครับเพื่อว่าผมจะได้ชัดเจนนะครับทุกวันนี้ก็ยังจำชื่อคนไม่ค่อยได้นะว่ามาจากห้อง605หรือ604นะครับโปรดอำนวยความสะดวกให้ผมนิดนึงครับ so this is M33, right? M33254, right? Which is held by อาจารย์ณัฐพล all right, yeah, thank you สุภวิทย์ like that ณัฐวินนี่ห้องอะไรณัฐวินห้อง605ใช่ป่ะ604ใช่ป่ะสุภวิทย์ like that yeah 605เข้าเซสชันนี้นับเป็นอีกครั้งหนึ่งของการเรียนนะครับโอเคเดี๋ยวครั้งหน้าเขาชดเชยยังไงเดี๋ยวก็นับกันอีกแบบหนึ่งนะครับเพื่อให้แยกให้เห็นชัดเจนนะครับก่อนหน้านี้กับอันนี้นะครับภวิทย์ชื่ออะไรวะนี่60อะไรช่วยพิมพ์ใหม่ได้ไหมผมรู้แต่ว่ากันตพลน่าจะเป็นห้อง604ภวิทย์นี่อะไรเอ่ยพฤตินันนี่เท่าที่จำได้605นะครับโอเคไหมOkay, let's get back to the story about quantum mechanics. And yeah, you have already seen K, L, M, N, O, P, right? And that's the shell state, right? Yeah, the shell number, right? The shell symbol. Okay. Here is the shell symbol, and here is the sub-shell symbol. All right. Yes. Yeah. Once you have generated the quantum state for many times, you'll be able to see the number of possible electrons to be filled in the subshell, like the K and L. Right. You would have two possible cases. Spin up, spin down, and the number of total orbits will be 2, right? Number electron filled in this shell will be 2, only 2, right? For L equal to 2, for L and N equal to 2, you have L equal to 0, you have L equal to 1, and that's 2 and 6. 2 and 6 will be combined to number 8, and that's the whole possible cases of electron orbits to this scenario. In when small n is equal to 3 or the capital M, you have L0, L0, L is 1, L is 2, 2, 6, and 10. You will get 18 like this, okay, and that's the whole possible, okay. And as you have seen before, right, here is the distribution. No, it's M605, right? All right, this is M605 already. And here you could see when n is equal to 2, you have 2, 4, 6, 8 cases, and here is the 8 cases. Here are the 8 cases from L, right? For L when n is equal to 2 นะครับพวก 605 นะครับวลินทรเนี่ยน่าจะเป็น 605 ประวิตรนี่ใช่ป่ะถ้าให้ดีช่วยพิมพ์ 605 ด้วยนะคนคือแค่สลับคนแรกครับกันตพล604 นะครับ alright yes and in the second case when in the second example when n is equal to 3 I have already shown that there will be 18 cases like this, and that's why we have all 18 possible cases for the electron to be filled in the shell of the atom, right? And when n is equal to 4, what else do you think then? Yeah, it's going to be 32, right? 32. What do you think then when n is equal to 5? KLMNO, okay? The O case, okay, when the shell symbol is O. How many possible electron orbits we could have in this scenario when n is equal to 5? What do you think? The way to deliver the answer to this question is a little bit complicated, and you could see it here. Not yet. Okay. 18, 32 in yeah. Another way to represent is that when n is equal to 1, you have LC, L as 0, ML will be only 0 in the spectroscopic notation. Okay, this notation is called spectroscopic, and it's 1s. Okay, it's 1s in yeah, the 1s is the case because n equal to 1 and the subshell is s, right? L is 0, and when n is equal to 2, which is L, the capital L case there, L is 0, it's called 2s, right? Because n is equal to 2. And when n is equal to 2, but L move from 0 to 1 is denoted by P. Is spectroscopic P case, and we have 6 possible value for electron orbits. So when we make the combination, when we combine these 2 and 6, we get 8 states. Okay, and this is KLMNOP, right? Yeah, that's the shell symbol KLMNOP. And for the case when n is equal to 3, there will be 3 possible cases for L, right? And start from 2, 6, and 2, 6, and 10, right? We combine all these 3 subshells, we will get 18 possible cases for electron orbits. All right, and that's the shell symbol M, right? When small n is equal to 3. When small n is equal to 4, we have the shell symbol capital N, and we have L equal to 0 until 3. And ML will be spanned from 0, -1, 0, 1, -2, -1, 0, 1, 2, and blah, blah, blah. Okay, -3 until number 3. And the spectroscopic notation will be changed also. Okay, this is 1s, but this one is not 1s, this is 4s because our n here is number 4, so we have to write down 4. Everywhere here is denoted by number 4. Okay. And the number of state will follow the same way. We have 2 because even we have a single case, we have 2 orbits because of the electron spin, right? Spin up and spin down, and that's why we have 2. Okay, double the possible cases here. This is 3, and we have to multiply by 2 because the spin number is 2, right? Yeah, you would observe that this is 32 cases for n equal to 4, right? Yeah, and that's the shell n. All right. The subshell name was assigned by spectroscopist. Okay, okay, here the meaning is right here. S comes from the word sharp. P comes from principle. Okay, SPDF. You may ask me what is the meaning. Sorry. What is the meaning of SPDF, right? And I said, no, I don't know the meaning why they say SPDFGH, but right now here, S stands for sharp, and P comes from the word principle. D came from diffuse. F comes from fundamental. Okay, and that's the meaning. The number of electrons allowed in subshell and shells from reference number 4. And shell number n, subshell name, and a number of possible electrons could be captured in this example is taken from book number 4. 1s2. Okay, when n is equal to 1 and when n is equal to 2, we have 2s2 and 2p6 because there are three values for ml, and there will be 6 orbits for the electron orbits when L is when L is number 1 here. Okay, and yeah, we would, when n is equal to 3, we have 3s2, 3p6, and 3d10. Okay, you combine the power number here, 2, 6, and 10, you get 18. For the case when n is equal to 4, you have number 2, number 6, number 10, and 14. You combine all these 4 numbers, you get 32. When n is equal to 5, K, L, M, N, O, P. Okay, this is O. Okay, the subshell notation is O here. Oh, sorry, the shell symbol is O. For number 5, we have 5s2, 5p6, 5d10, 5f14, 5g18, and we get after the combination of these 5 numbers as 50. So there will be 50 electron orbits or states in this scenario. Okay, when n is equal to 6, there will be 6s2, 6p6, 6d10, 6f14, 6d18, and 6h22. And after the combination of these 6 numbers, 2, 6, 10, 14, 18, 22, we get at the end 72 electrons. Okay, in the whole shell here. Okay, and you may ask me, so how could we get this number? Is there any formula for that? So what is the time we need to finish? Is 16, so it's 1550, right? 1550. Okay, still 25 minutes. Yeah, is there any formula to get the result of number 2, 8, 18, 32, or 50, and 72, or should we memorize it in our head, in our brain? There we okay, yes, we will yeah, we will see what or how the scientists capture the formula, the expression in terms of n here. Okay, n. Once you know the maximum number of allowed electrons can be found from this one. Okay, Ne is a number of electrons. Okay, with the function of as the function of the small n, right? It's 2 plus 2 and 6 plus 2. This is the state of n equal to 1. Okay, this is the K shell. Okay, K shell. This is the L shell, okay, when n is equal to, when n is equal to 2, it's called L shell. When n is equal to 3, it's M shell. Okay, this is NOP, blah, blah, blah. Okay, SPDF. Okay. For n equal to 1, we have only L equal to 0. For n equal to 2, we have L equal to 0 and L equal to 1. For n equal to 3, we have L equal to 0, L equal to 1, and L equal to 2. And you just make the combination to 16 is 18, 8, and 2, and blah, 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 right? And once we make the expression of the combination, we get the summation expression here. And when we distribute the summation notation to each term, we get this one in terms of n. And once we combine everything, we get 2n squared. Okay, you could see that 2n squared should be valid to 2n squared should be valid to all of these, right? For example, 2n squared, right? When n is number 1, it's going to be 2. When n is equal to 2, 2 squared is 4, 4 times 2 is 8, right? It's 8. When n is equal to 3, 3 squared is 9, 9 times 2 is 18, right? When n is equal to 4, it's 16, 16 times 2 is 32. When n is equal to 5, 5 squared is 25, 25 times 2 is 50, and that's why we have 50 for 5. When n is equal to 6, 6 squared is 36, 36 multiplied by 2 is 72, okay? And you get the whole thing here on the right-hand side and the last column, 2, 8, 18, 32, 50, 72, okay? So 2n squared is valid if you wanna find the possible orbits of the electron around an atom. All right. Yeah, this is the formula, final formula, if you want to find the number of possible orbits of the electron in an atom. And in chemistry, they use a different way to express the electron orbits. Okay, and that principle is called Aufbau. Okay, Aufbau principle. I would say that Aufbau is the word in German. Okay, the language speaking in Germany. Aufbau means building to it, building on top of that, or something like that. The meaning in English. Okay, but simply speaking, it's called Aufbau principle. It means that you start from 1s. Okay, when n is equal to 1, okay, it's a zigzag movement like this, okay, but it's not in horizontal way, it's not in horizontal way or vertical way, it's the mix, okay, horizontal is the zigzag way. When n equal to 1, you have 1s, okay, when l is equal to 0, and you move in the zigzag way to n equal to 2 and l equal to 0, you have 2s. You move in a zigzag way to L equal to 1, but for case n equal to 2, and you go further to 3s. Okay, and you move back to 3p when n equal to 3. You move further to the next case when n equal to 4, but L is equal to 0. You move to 3d. Okay, for the case when n equal to 3, but L equal to 2. You go to 4p when n equal to 4 and L equal to 1, and n equal to 5 and L equal to 0. You get something like that. And you move back here to 4d when n equal to 4 and L equal to 2, and L equal to 1 and n equal to 5. Okay, 5p is known as 5p, and here we have 6s and blah blah blah. Okay, and 4f, 5d, 6p, 7s, blah blah blah, 5f, 6d, 7p, and 8s. Okay, the way you move in this way, in this orientation is called it lies in the outbound principle. Okay, I didn't discover or set up this system. Okay, it's taken from the scientists, from the physicists. And the number of electron field in the subshell and shell could be also represented like this. When n is equal to 1, you have 1s. When n is equal to 2, you have 2s. Okay, the nucleus is over here. This is the first layer, the second layer, and the third layer, and so on, right? And in this layer, there will be 2 subshells according to the spin up and spin down configuration of energy level. You have n equal to 2, n equal to 3, okay, 3s, 3p, and 3d, right? And 4s is lower than 3d actually, and 4p is a little bit higher than 3d, because you go along this way. Okay, you first meet 4s, yeah, first 4s and then 3d. Okay, 4s and then 3d. So 3d is higher than 4s. Okay, even it is d. Okay, but is the higher according to this orientation. 4d is higher than 5p. Okay. Sorry, is lower. 4d is lower than 5p, but 5s, okay, 5s here is before 4d, so it's lower than 4d, and so on. Okay, and the notation of 36 here, figure 36, has some relation to this one, and this is in German. Okay, I'm sorry for that. It's taken from the German book. It's orbital energy, so you could understand in English, right? It's orbital energy. Okay, this is taken from the book in German, and yeah, you see it, so on and so on. Okay, when n equal to 4, when it is equal to 4 to 5, 6, and 7. Okay, it doesn't mean that when n is bigger, the energy level will be always higher. It depends on the route you move in this outbound principle. Okay, the Pauli, now we arrive at the Pauli's general exclusion principle. As I told you, Wolfgang Pauli is an important person. Where is that? No. Where is that? Oh, here. Yeah, Wolfgang Pauli. Where is it? Wolfgang Pauli is an important person. Okay, he doesn't only discover the spin idea of the electron, but also discover the Pauli exclusion principle, or simply speaking, it's called Pauli principle. Okay, but actually it's exclusion principle, or simply merge these two words. It's called Pauli exclusion principle. It means that okay, let's talk about his life. He is an Austrian who studied physics, okay, and works in physics, and he is the leader in physics, in quantum physics. Okay, yeah, in his idea, not only for electron. Okay, Pauli exclusion principle says electron could not locate at the same level. Okay, in 4p we cannot have in 4p there will be 2 splitting energy level, right? When for the spin up level and spin down level, and in this spin up and spin down, the electron could not stay more than 1 in each level. Okay, it means we could not find 2 electrons in the same energy level or greater than 2. Okay, it means electron will stay at the unique, okay, unique or the level that is different from the other. Yeah, that's the Pauli's principle. That's the Wolfgang Pauli's exclusion principle for the electron, but his principle doesn't state only electron. Is not valid for only electron, but also valid for the other subparticles like fermions, right? You know fermion, right? If you can still remember, we have already seen the subatomic particle here, elementary particle in this table, right? It's standard model of elementary particles. Fermion is this one. Okay, the blue, the pink, oh no, the violet one here. Okay, we have quarks, right? Quarks. Fermion contains also leptons, and before that, Pauli says electron could not have the same quantum state. Electron cannot stay at the same energy orbit. Okay, and that's the basic Pauli's exclusion principle. But it's not the case. Pauli said that not only electron, everything in this group, okay, which is called fermion. The fermion cannot stay at the same energy level. It means they cannot have the same quantum number. Okay, quantum number, what is that? Principal quantum number, orbital quantum number, magnetic orbital quantum number, and spin up, spin down quantum number, spin number. All right, spin magnetic quantum number. Full name for that. Yes, Wolfgang Pauli says his general exclusion principle state that no 2 fermion can be in the same quantum state. Fermion is the particle with spin number 1/2. Okay, you know that electron can have spin number 1/2 and -1/2, right? But other fermion may have spin number which is not 1/2. It could be also 3/2 and so on, like not this one, right? Yeah, the particle that has spin number 3/2, I still cannot see one of that. Kr, yes, can be in the same quantum state. Okay, the fermion with spin number 1/2 or 3/2 cannot be in the same quantum state. The wave function, which is denoted by the psi, okay, psi, psi function, which is a function of the coordinate on x, coordinates y, coordinates z, and a function of time, for a particle contains all the information that can be known about dynamic state of that particle. Okay, let's introduce the wave function. Now we are going to see the Schrödinger's wave equation. Okay, yes, wave function is related to, okay, the wave function is not the deterministic function that will tell you where the particle is. Okay, it's only the probability. It's because when the particle is very tiny, it's very hard to see the actual location of that particle. So what the human could try to guess is only the probability. Okay, so the wave function is only the probability function. The probability of what? The probability of finding the particle in each of various regions. If the particle has a charge, the wave function can be used to find the charge density at any point in the space. Okay, the wave function can be used to find the average position of the particle. Okay, because it's the probability, you just make the expectation. Okay, expectation is the mean or the average. You could find the average velocity. You could find dynamic quantities like momentum and energy. Okay, so wave function is quite useful to describe the tiny particle. And the wave function, also the angular momentum, you could be found from the wave function. The wave function is actually the complex function, and what we could see is only the magnitude. The magnitude of the wave function is shown here when for the 1s state. Okay, when the electron, or when n is small n is equal to 1 and L is equal to 0, you get the plot in side view like this, and here is the top view. You could see the density around the center because it has high value. The magnitude of the wave function is high at this value, the origin, right? You have the density at the center, and for the 2s, when n is equal to 2 and L is equal to 0, you have high density to find the particle at the center and also around the center in this circle. And for the case when n is equal to 3 and small l is equal to 0, you have high chance to find the particle at this location. You have high chance to find the particle at this location. You have high chance to find the particle also at this location. It doesn't mean that you will find exactly the particle, okay? It's only the chance or the probability to find that particle, because once we are talking about something very small, very, very tiny, very small, it's very hard to predict the actual location. And what the human could see is only the probability of prediction. Okay, Schrödinger equation, as it is called, was developed by Erwin Schrödinger. Oh, who is that? Let's take a look at this person. Erwin Schrödinger. Erwin Schrödinger. This person. Okay. In English version. Okay, Erwin Schrödinger. This guy. This person. Okay, Erwin Schrödinger. Oh, his name is very long. Erwin Rudolf Joseph Alexander Schrödinger. Okay. He got the Nobel Prize too. Okay, he is the Austrian and Irish. Okay, he sometimes live in Ireland, but he is actually from, I don't know, from Austria-Hungary, from Vienna, but he spent some time in Ireland, so he got the citizenship of Ireland too, which is Irish. Okay, that person, the Erwin Schrödinger guy, have set up the equation to predict the particle given physical situation, and the wave function that solution of this equation represent various possible physical state of the system. Okay, yeah, he developed the problem and he also derived the solution. Okay, and for an electron in a hydrogen atom in a state with energy En and quantum number n, the acceptable solution of Schrödinger's equation exists only when the magnitude L of the vector angular momentum is L. This is the vector version of the angular momentum, okay, which is denoted by L, will be equal to square root of L times L plus 1 and times the h slash, okay, h slash is h by 2 pi. When L start from 0 to n minus 1, okay, that's the orbital quantum number, right? That's the conventional way of the orbital quantum number for us in quantum mechanics. Okay, this is the result from Schrödinger. All right, what is that? And another one, okay, this is the vector angular momentum. Another one is the angular momentum and magnitude, the magnitude of the angular momentum. This is the vector one along the z-axis. Oh, this is the magnitude L of the vector angular momentum. This is the angular momentum magnitude along the z-axis. Okay, can be only Lz equal to ml. Ml is the orbital magnetic quantum number. Okay, the third quantum number, right? ml times h slash. Okay, and ml could be 0 plus minus 1 plus l minus 1 plus minus l, right? In if you take a look at the result from the Schrödinger wave equation, you could see here is the Lz. Lz is yeah, the result here is L. This is the case when L equal to 2, right? Lz equal to 0, L equal to 2h, L equal to h slash, right? 2h slash minus h slash minus 2h slash. That's the result from the here. Okay, you just multiply h slash by the value of ml, you get the value of the angular momentum magnitude along the z-axis. And here is the vector angular momentum magnitude L, right? This is also Lz vector. This is the magnitude. 2h slash h slash L0 minus h slash minus 2h slash. And yeah, consider a hydrogen atom in a state with n equal to 4. Find expression. Here is the first example about the hydrogen atom. Okay, in a state with n equal to 4. Okay, it's a what is that? K L M N. Right? This is the capital N shell notation, right? Find the expression for the largest magnitude L of angular momentum. Find the largest positive value of the Lz, which is the angular momentum along the z-axis. And the corresponding value of the quantum number L and ml. Okay, and for the corresponding quantum state, find the smallest angle that the angular momentum vector can make with plus z-axis. Okay, this is so there are two main sub-problem, sub-problem, right? Okay, when n equal 4, I'm not sure whether we could finish this one. Okay, we will finish this chapter soon. Okay, when we start with n equal to 4, right? The largest magnitude L will be max of L. Okay, we start from this expression here. Okay, equation number 82, and we try to maximize the value of L. So the right hand side is substituted, is used later. Okay, max when L from 0, 1, 2, 3, right? Because 4 minus 1 is number 3. And find the best combination that will provide the maximum value to the square root. We find that for the case when L is equal to 3, we get square root 12, and we get square root 12 times the h slash, right? The angular version of the maximum constant. We have 3.65 times 10 to the negative 34 joules second, and that's the largest magnitude of the angular momentum from the state n equal to 4. For the largest positive Lz, that's the angular momentum along the z-axis. So this expression, we're going to use this expression because they want to know the maximum value, the smallest, right? The smallest. So we have to maximize maximize. So 0 plus 1 minus 1 plus 1 minus 3, right? There are L plus 1 cases, right? Small L plus 1 cases. So ML, the maximum value will be only the positive one, which is 4 minus 1, right? And 3 h slash. And yeah, when we substitute the h slash, we're going to get 3.16 10 to negative 34 2 seconds. And for the small rectangle, we're going to have theta mean. Theta mean will be across LZ by L, because if you take a look at this, the cosine is the ratio between LZ and the absolute of vector L, right? LZ by L, right, which is the length of this vector. So LZ by L, and theta mean will be the 3h slash, which this one, right, 3h slash by this one. Okay, the denominator is the maximum one, and the numerator is also the maximum one. We get across 3 square root 3 by 2, which correspond to 30 degrees. Okay, and the lecture of today has to finish because the time is over right now. So M605, see you tomorrow. In the next chapter, we have finished the chapter number 6, atomic physics right now. Okay, พบกันวันพรุ่งนี้ครับ M605 นะครับ ใครมีคำถามโปรดถามนะครับ เดี๋ยวผมจะแคปเจอร์หน้าจอสำหรับคนที่เข้าเรียนวันนี้นะครับ see you tomorrow บ๊ายบายครับ สวัสดีครับ